Hello everyone, my name is Saran Ratanakowit and today I will present my finite element analysis project titled Structural Analysis of a Four-Bladed Helicopter Rotor System using ANSYS Mechanical APDL. The objective of this project is to investigate the structural behavioral of a simplified helicopter rotor system under aerodynamic loading and to compare the performance of three different finite element formulations available in ANSYS mechanical APDL, namely solid 185, solid 186, and solid 187. Helicopter rotor blades are responsible for generating lift and maintaining flight stability. During operation, the rotor system is subjected to significant aerodynamic forces, which produce deformation and stress within the structure. Understanding these stress is important because excessive deformation or stress concentration may lead to structural failure, especially near the blade root connection. Therefore, the objectives of this project were to develop a simplified helicopter rotor model in ANSYS APDL, investigate its deformation and stress behavior, compare different element formulations, and perform a mesh convergence study to determine which element provides the most reliable results. For the FEM model development, this slide shows the rotor assembly consists of four rotor blades, a root grip block, a central hub, a mast, a blade base plate support structure. The model was intentionally simplified to focus on the structural behavior rather than the aerodynamic shape optimization. The material selected was aluminum alloy 10601T6, which has a Young modulus of 69,000 megapascal, a Poisson's ratio of 0.33, and a yield stress of about 270 megapascal. The analysis was performed using Newton millimeter megapascal unit system. Now for the boundary conditions and loading. The bottom face of the base plate was fixed in all translational degrees of freedom, meaning that Ux, Uy, and Uz were constrained to 0. A uniformly distributed pressure of 0.002 megapascal was applied to the rotor blade surfaces to represent a simplified aerodynamic loading condition. The total blade area is 400,000 square millimeters, resulting in an equivalent of aerodynamic force of approximately about 800 newtons acting on the rotor system. In this project, three different finite element formulations were compared. Solid 185 is an 8-node linear structural element. Solid 186 is a 20-node quadratic element. Solid 187 is a 10-node quadratic tetrahedral element. The purpose of comparing these elements was to evaluate how element formulation influences convergence behavior and numerical accuracy. Higher order elements generally provide more accurate results, but require greater computational resources. Now, this slide illustrates the meshing strategy used throughout the study. A free tetrahedral mesh was selected because the helicopter rotor assembly consists of several connected three-dimensional components and contains geometric intersections that are difficult to mesh using structured methods. Several mesh sizes were investigated. For solid 185, mesh sizes were from 30 millimeters down to 8 millimeters. For solid 186 and solid 187, mesh sizes from 30 millimeters down to 10 millimeters were evaluated. These mesh refinements were later used for convergence analysis. This slide presents the displacement convergence results. The graph for solid 185 shows that the displacement continued increasing as the mesh became finer. Therefore, full convergence was not achieved within the investigated mesh range. In contrast, solid 186 and solid 187 produced nearly identical displacement values, as the mesh was refined, indicating converged solutions. This demonstrates that the higher-order elements provide greater numerical stability and require less refinement to achieve convergence. The key finding here is that solid 186 and solid 187 converge, while solid 185 remain mesh-sensitive. This slide presents the stress convergence results. Unlike displacement, stress values remain sensitive to mesh refinement. For solid 185, the maximum 1 mesostress increased significantly from approximately 8 megapascal to nearly 19 megapascal as the mesh became finer. For solid 186 and solid 187, produced higher stress values reaching approximately 30 MPa at the finest mesh. Although complete stress convergence was not achieved, the stress distribution consistently identified the same critical regions within the structure. Therefore, displacement was selected as primary convergence criterion. For the numerical results, solid 185, the maximum deformation was approximately 9.52 milliliters, and the maximum stress was 18.68 megapascal. For solid 186 and solid 187, the maximum deformation was approximately 12.99 millimeters, and the maximum stress was 30.42 megapascal. An important observation is that solid 186 and solid 187 produce identical results, which increases confidence in the numerical solution. For the deformation and stress contours, the deformation plots show that the largest displacement occurs at the blade tips. This is expected because the blades behave similarly to cantilever structures subjected to distributed loading. The stress contour indicates that the higher stress occurs near the blade root and the hub connection region. These locations transfer loads from the blades into the central structure and therefore experience the largest bending moments. Consequently, the blade root and hub connection are identified as the most critical structural regions. In conclusion, finite element analysis was successfully applied to evaluate the structural behavior of a simplified helicopter rotor system. The displacement convergence study showed that solid 185 did not fully converge, while solid 186 and solid 187 achieved converged solutions. The maximum deformation obtained was approximately 12.99 millimeters, and the maximum 1 mesostress was approximately 30.42 megapascal. The critical structural region was identified as the blade root and hub connection. Using the material yield strength of 276 megapascal, the calculated factor of safety is approximately 9.1, indicating that the structure remains well below yield limit under the applied loading conditions. For future work, the model could be improved by incorporating realistic airfoil geometry, blade taper and twist, composite materials, rotational loading, model analysis, and fatigue analysis. Also, to answer some questions in advance, so some questions such as why did solid 185 did not converge? So the linear formulation requires significantly finer meshes. The ANSYS student version that I use has a limited further mesh refinement. And another question would be, why are solid 186 and solid 187 identical? Both are higher order quadratic elements. The identical results indicate that the solution is independent of the element formulation and therefore reliable. This concludes my presentation. Thank you for your attention.